My name is Tet Evans and I'm the lead FEA engineer at Evotech CAE Ltd. This video makes up a tutorial from the 101 series and is focused on a number of aspects of 3D tetrahedral element modelling and FEA within Apex. Okay, so in this tutorial we're going to look at 3D modelling and FEA using tetrahedral elements. Now these elements are useful for the 3D modelling and meshing of complex shapes. So you can see here for this aerospace bracket we've got lots of fillets, lots of hole detail that would be difficult to capture with anything other than a 3D element. So first of all we're just going through the model, running through measuring the wall thicknesses. So we can see we've got a standard 5mm wall thickness for the thinner regions, so that will enable us to guide the downstream Tet meshing geometry or Tet meshing size. So once we've got those an idea of the appropriate size that we're going to use, we can go into the solid mesh form, input a reasonable mesh size, so we're putting in 2.5mm in this case, element type, so we're using quadratic, so Tet 10 element with mid-side nodes. We've got curvature refinement and some other solid mesh controls defined in this form. So we simply select the solid mesh, the solid geometry of interest, and run through the meshing algorithm, and we can see the resultant mesh on screen. We can look at element quality. So again, similar to some of the other tutorials, this time we're looking at quality in 3D. So with that turned on, we can look at aspect ratio or element Jacobian to understand any areas where we've got poor mesh definition. So again, the bulk of this model is good quality. We've got some bad elements, so we can show only those bad element regions along with the underlying CAD definition or the 3D CAD definition, and we can see in this region we've got sort of manifold edges coming together for two different fillets and one of the surface edges. So maybe the 2.5mm edge length is not appropriate in that region if it was a region of interest, but certainly we don't have any invalid elements. So some different techniques now where we can look at refining the mesh in areas of interest. So what we're going to do now first of all is surface mesh using the standard surface tools some faces of the solid, so in this case the fillets shown highlighted in this selection, and we can pick those regions, middle mouse to accept, and we've got a 1mm element edge length in these regions. So with that surface mesh defined, seed mesh effectively, we can go back into the solid mesh algorithm with the 2.5mm element edge length, and we mesh the structure, but it respects the 1mm surface edge or surface detail at the fillet features where we wanted a finer mesh definition. Okay, so that would work nicely for lots of structures, but obviously if you've got lots of fillet detail, chamfers, holes, that type of thing, then you may find a lot of work is required in defining those 2D surface meshes in the first instance. So Apex has a different tool that we can use, feature recognition. So what we're doing first of all is just highlighting, using the standard geometry defeature tools, some typical dimensions for features that we might be interested in. So we can see here we've highlighted all the smaller fillets in the model, and we can measure those accordingly to drive the feature mesh settings that we'll come on to in a moment. So you can see we can turn on the feature mesh checkbox within the solid mesh tool, and that will reflect all of the features that we've defined. So we've got fillets, chamfers, cylinders, washers, etc. So first of all we're going to put in a fillet mesh control. So we can see we've got the ability to control features of different sizes. So we've set a control in here to say that fillets with a radius of 4mm or less will have a particular fillet feature definition in terms of the downstream mesh, and equally washer, which is effectively the hole around a given the ring of elements around a given surface, or hole I should say. We're going to put in an angle constraint, so we're going to put in an angle of 15 degrees and a width control of 2.5 millimeters with 2 rings of elements around each hole within the model. Okay, so once those are defined, so in this case we're looking purely at fillets and washers around holes. So we go back into the solid mesh algorithm, again Tet 10 algorithms, quadratic element, with the fillet and the washer checkbox turned on. And if we inspect the resultant mesh, we've got again washers around holes, so 2 rings of elements, and a controlled angle around the fillets. For the larger holes, we have a different washer control, and for the larger fillets we have a different different element size control. So we can turn the element quality fringe plot back on and understand where we've got any potential issues with the mesh quality. Again, the bulk of the structure is shown as good in this instance, but if we highlight one particular area of interest, which might be this this fillet shown at the moment, our feature mesh settings did a good job of getting 4 elements around the circumference of the hole, but the fillet I should say, but maybe not getting the aspect ratio that we want. So what we can do is define a live edge seed, which gives us a better control and ultimately better quality for the resultant mesh. So we're now going to look at a different technique called partitioning, which allows us to break up a solid into different partitions or regions which we can mesh separately. So first of all, we're going to define some cut plane geometry or cut surface geometry using the sketcher tools and some simple transformations in Apex. And again, we're basing this on the very easy user feedback in terms of display and model control. So we're just simply moving 2 surfaces into position and generating another surface in the secondary plane. So simply using the sketcher tools again. Coming out of the sketcher, we can see we've got the surfaces required. Again, transforming those surfaces normal to the plane we've just created. Ultimately, these surfaces are going to be used to partition the underlying solid, which we'll see in a moment. So dragging those surfaces into position and changing the colours within the model browser, we can see the cuts that we're going to make on the underlying surface. So back into the standard geometry tools, so the split tool, so we're going to split using a surface, and with the option set to partition, so this actually partitions the solid but doesn't break it into separate solids, so it allows us to generate these partitions which will then be respected by the subsequent meshing operations. So in other words, controlling the interface between partitions of a given solid to ensure we've got mesh congruency and a good flow of mesh transition across the interface. So if you show it in wireframe, you can see the dotted lines highlight the partition. We've still got a single solid as shown in the model browser tree, so we can go back into the solid mesh tools, set the mesh size in this case to 1.25 mil, and select the filter, rather set the filter to partitions, and we can mesh a portion of a solid discretely from the rest of the solid, and therefore have total control over what the mesh is doing. So unlike the surface seeding approaches that we looked at previously, partitioning actually controls the element size going into the solid geometry that's being meshed. So ultimately we end up with a better control on the surface and also through the thickness of the solid, or going into the thickness of the solid. So we can see here the partitions now, all the partitions for a given mesh are fully defined, and we can see the transition from 1.5 mil to 2.5 mil across this fillet interface. We can make these partition cuts in any region that we might be interested in, and some simple quality controls to make sure that the mesh is ended up in the way we want it. So once we've got the solid meshed and feature recognition set, we can then do our standard geometry operations. So here we're simply modifying the diameter of a given hole using the push-pull tools, and we can see the mesh is updated and still held onto the feature mesh settings. We can do it on a manual approach, or we can record a macro to allow us to automate the full modification that we want to make and store it in a macro. So here we've got lots of holes, a typical aerospace application where we may have a Mark II geometry which is based on a different fastener size, a different hole diameter size. So again, we're simply recording a macro, highlighting the push-pull or hole increase that we're interested in, and we can then stop that macro, and now we can go into the macro settings. So Apex uses a Python interface or Python API, and this is the raw macro that's come from the interface showing the operations that have been performed. And if we look in there, we can see the push-pull distance set explicitly. So a modification we've made, so basically we've edited the macro, and we've put some logic in there that defines the starting hole diameter, the end hole diameter. We put a little message in to make sure the operation, or to highlight that the operation has worked as required, and we've parameterized the hole distance. And then we can now go back to the original geometry, play the macro, select the macro that's been edited, run it. The mesh is updated. We get a little message box appear to say that the macro is run accordingly, and the geometry edits have been made. The mesh is updated. We can zoom in again on those features and see that the structure has been updated. So once we're happy with our mesh, we can run Apex in the standard manner, either on a static or normal modes for verification, or any of the other of the analysis types that we want. In this case, we're looking at a linear static output, some simple stress output requests, and we've got our standard outputs again. So we've got invariants such as von Mises and principles, and we've also got components in any system that we might be interested in. So looking in this particular region and looking at von Mises stress, so we can turn the averaging, which is effectively the average between solid elements at a given node, we can turn them on and off, and we can look at a difference plot, which is a good measure of understanding whether our mesh quality is appropriate in that region. Okay, and thanks for watching this tutorial. Be sure to keep an eye out for the remaining tutorials in the 101 series to illustrate how Apex can help you with your FEA process.